Suppose T is an element of the set of all linear transformations from F2 to F2 defined by T that maps all ordered pairs of W and Z to ordered pairs of minus Z and W. Find the eigenvalues and eigenvectors of T if F the field equals C the set of all complex numbers. Okay, right. To solve this problem, we begin as follows. So we start by saying let T of W and Z, which equals lambda of W and Z. Okay, so what is the meaning of all these? So this means we remember that T is minus Z and W, so that here we shall put minus Z and W, like so, which equals lambda of W and Z. So what is this? So this actually obviously tells us that minus Z and W is actually equal to lambda W lambda Z, like this. Right, from that we're able to see, so that implies that what we have is that minus Z is equals to lambda W and W is equal to lambda Z, like so. Now, if you have to call this one equation 1 and you have to call this one equation 2, we can then proceed to say this implies that we can then say put 2 into 1. Put 2 into 1. Minus Z equals lambda. Okay, so W is lambda Z. So we have lambda Z, which means Z equals lambda squared Z. Right. Well, we note that at this point, Z is not 0, because if ever it would happen that Z is 0 here, W is going to be 0 as well. If Z is 0, W becomes 0 in equation 2, and that means we have a 0 eigenvector, which is not the case. So we can divide through by Z, getting lambda squared equals that, which means lambda is plus or minus I. Plus or minus I. Okay. These two are actually what we call the eigenvalues. Eigenvalues. Right, so these are the eigenvalues, and it remains for us to find the eigenvectors. So how do we get the eigenvectors? So we get the eigenvectors as follows. Right, so for us to obtain right now what we call the eigenvectors. Eigenvectors. So would have therefore that from this point, for example, at the point that we have Z. Z is lambda W. Okay, if Z is lambda minus Z, minus Z is lambda W. And that means that Z is minus lambda W. So we have two cases, for example, for For lambda equals I, we have that Z equals minus IW. And if this is true, we have that then we have the following. Then we have the following. Right. It follows then that we have, for instance, the eigenvector WZ, or W and Z becomes W, and Z is minus IW. Factor out W, 1 minus I. 1 minus I. Okay, just writing lambda there, but it should be I. So we have 1 minus I. Right. Similarly, for lambda equals minus I, because there are two eigenvalues, it will follow, therefore, that Z, which is equals to minus lambda W, you substitute lambda equals minus I in there, giving us IW. Then the eigenvector W and Z would be W. Z becomes IW, which becomes W into 1 and I. And now the conclusion, therefore, is that hence the eigenvectors are two of them. They are 1 minus I for lambda equals I. And so you have 1 and minus I, but the 1 minus I eigenvector corresponds to lambda equals I. And we have the other one, which is 1 and I for lambda equals minus I. Okay, in which case, therefore, we are done with solving the problem, because the question was find the eigenvalues and eigenvectors. We've seen that the eigenvalues are plus or minus I, and we've seen that the eigenvectors are 1 and minus I for lambda equals I, and the other eigenvector is 1 and I for lambda equals minus I. So thanks, everybody. Goodbye to you.